This video is going to be about properties of waves. Transverse waves, which we said in the last video, are going to be waves that go up and down, or actually I have a picture of them like this. So as the wave propagates from left to right, the molecules move up and down perpendicular to that. Transverse waves have high points called crests. So that would, for example, be these sorts of points here. And also troughs, which would be these low points, sort of the opposite of a crest. Compressional waves, on the other hand, have neither of those. It does have areas where the waves are more condensed, sort of like these areas that I'm circling at the moment, versus areas where items are more spread apart, which is sort of the similar idea. All waves will have something called a wavelength, which is represented by this lowercase Greek letter called lambda. Wavelength is going to be the distance between one point on a wave and the nearest point just like it. So for example, in our image here on the bottom, let's say if I start my wavelength there, my wavelength does not go from this point to this point that I marked with an X. It doesn't go there because that's not just like it. If you think about the way the wave is moving, I'm going up, then down, then up again. So my wavelength will actually go from this point to this point D over here, because here I was going up when I got to that point. Here I'm going down. Therefore, it's not just like it. It might be the same place, but it is not just like the one that I had before. Okay, let me sort of get rid of these. So my wavelength, for example, an example wavelength on this would be from D to G, or from A to E, for example, or even from B to F. Those are all possible wavelengths where they're exactly just like it. The frequency, or lowercase f, is going to be the number of wavelengths that pass a specific point each second. So say I'm here and I'm watching letter C, and waves are passing me and passing me and passing me. I will count the number of waves that pass. So I might, especially C is easy, so every single trough that occurs, I will count how many of those pass each second. And the units of frequency are in hertz, which is a capital H and then a lowercase z. This is our first unit of the year, which has 2 letters to it. So you could, for example, have something that's a gigahertz, that would be a capital G, then capital H, and then lowercase z, just like we have other metric prefixes. A frequency of 1 hertz basically means that one wavelength passed by in 1 second. So that is how frequent the waves are. The period then is the amount of time it takes one wavelength to pass a specific point. Okay? So, for example, I might say, okay, if I'm looking at this point, how long does it take just one whole wavelength to pass that point? Okay? So therefore, as frequency increases, right, that's basically how fast I'm moving. If frequency increases, period decreases. If it's very, very frequent, the amount of time that one wavelength takes to pass is going to be very small. So as frequency goes up, period goes down in the units of a period, or in seconds. Wavelength, as you could also imagine, is inversely related to frequency. What that basically means is also similar to frequency and period being inversely related. As wavelength goes up, frequency goes down. Similarly, if wavelength goes down, frequency goes up. For example, here we have sort of the same time frame for these waves. I have a long wavelength here, but in terms of how many waves pass this point in an amount of time, I have very few waves in this whole section here. Here my wavelength is now decreased a little bit, and I'm fitting now more waves in a specific time. In my third example, I have an even shorter wavelength, and therefore the frequency that my waves are coming, especially because they are closer together, because they have a shorter wavelength, I now have a shorter wavelength equals higher frequency, longer wavelength equals shorter frequency. We can also talk about wave speeds. We talked about the wavelengths, we talked about the frequency by which the waves come. We also talked about the period of the waves. Wave speed is basically going to be the frequency multiplied by the wavelength, but I do want you to know that wavelength depends on the medium through which it is traveling. Some waves will be slower between mediums. In fact, it might, when it transfers from one medium to another, it might slow down or it might speed up depending on which direction it's going and which medium has certain properties. The other thing that you need to know that as the temperature of the medium increases, so does the frequency. And when we talk about thermal energy and what does it mean to have heat or have high temperature, you'll understand more about molecules moving in the medium and things like that, and why then the frequency increases later. But what you need to know for now is that the speed equals the frequency times the wavelength here, or you have this equation with sort of shorter letters. The last sort of property of waves that you need to know about is the amplitude. And the amplitude is basically going to be the distance from the crest or the trough of the wave to the rest position. So you can consider the rest position to basically be this middle line that you can draw about halfway through. And the amplitude is going to be the distance between the crest and that resting point, or the trough and that resting point, and it will be the same. So it doesn't matter which one you take. And amplitude is going to be related to the energy carried by the wave. So the greater amplitude equals greater energy. So here on the left, we have a low energy wave. It has amplitude, but not nearly as high as the high energy wave over here, which has a larger amplitude.